Covalent bonding, part 7. Particle structure and macrostructure, or large-scale structure of covalent compounds and their resulting properties, along with a review of metals and ionic compounds. Let's begin with a review of metals. When a metal combines with another metal, that would be an element with low electronegativity, low attraction for bonding electrons, combining with another element with low electronegativity, low attraction for bonding electrons. The result is metallic bonding. This can be explained with the sea of valence electrons theory. And it works for a pure metal as well as a mixture of different metals, or an alloy. Let's consider a pure metal. Let's say that we have iron atoms combining with other iron atoms. Because they're metal atoms, they have low attraction for bonding electrons, low electronegativity, and their valence electrons pass easily back and forth between the atoms. Now notice that when we have an atom that loses an electron, it becomes positive, and we would call that a positive ion or a cation. And because these electrons are moving back and forth between the atoms, the metal cations, Fe+, are floating in a sea of valence electrons. And that results in these four properties of metals that we observe on a macroscopic or large scale. Number one, metals are malleable, they bend. Number two, metals are ductile, they stretch. And this is when we put them under stress. Imagine that we put some stress on the piece of iron at the end. What happens is the valence electrons flow between the positive ions, and they allow the positive ions to attract the electrons in between. And that keeps the iron together in one piece. With an ionic compound, when we put stress on it, the positive ions and negative ions come in contact with each other and opposite charges repel, so an ionic crystal gets broken apart, it's brittle. But with metals, we can see that as we put stress on the end of the metal, it will just bend or stretch. Now that means we can also smooth out the surface of a metal so that a smooth surface will reflect light with regular reflections, and we'll see a shine to it, or a luster. The fourth property of metals is that they're good conductors. They allow electricity and heat to flow. If we push electrons from an external source onto this piece of iron, those external electrons will repel the electrons that already are here, and in turn they will repel electrons further down the line. That's electrical conductivity. Heat is an expression of the movement of the particles. So if we bring something with high temperature, in other words, we add some heat to the end of this piece of iron, the particles on this end will begin to vibrate, and that will cause vibration to travel across these particles. That's thermal or heat conductivity. So we can explain the large-scale or macroscopic properties that we observe for substances based on the way that the particles behave, based on the properties of the particles. Let's take a look at how that works for ionic bonding now. When we have a metal with low electronegativity, low attraction for bonding electrons, combined with a nonmetal with high electronegativity, high attraction for bonding electrons, the metal loses electrons and forms a positive ion, and the nonmetal gains those same electrons and forms a negative ion. Oppositely charged ions attract according to the law of electrostatics. Opposites attract. And this is known as ionic bonding. The result is an ionic compound that's made of a crystal of ions. Consider this drawing I have here for a sodium chloride crystal. The positive sodium ion is ionically bonded to a negative chloride ion, and that's ionically bonded to another positive sodium ion, ionically bonded to another chloride ion, and so on. And we get this three-dimensional structure known as a crystal. Now, two important points about this. The bonds between these ions is the strongest bonds that we know that happen between ions. That's ionic bonding. And notice this chloride at the center is bonded to the sodium ion to the left, to the right, on top, on the bottom, in the front, and in the back. There's multi-directional strong bonding going on here. And as a result, we can observe macroscopically on a large scale these four properties of ionic compounds. They're solid crystals at room temperature. They have high melting point. In fact, molten lava is melted ionic compounds. You have to get ionic compounds as hot as lava to get them to melt. If you tried to melt sodium chloride on your stovetop, you would melt the pan that it's in, you would melt the stove, probably burn your house down before you could melt this sodium chloride. There are some industrial processes like glass making where we do use some molten ionic compounds. And we know that when you melt ionic compounds, what happens is these ions break apart from the crystal and become liquid, and liquid particles flow. So when we have positive and negatively charged ions that can flow in a liquid, well, that allows for conductivity. So ionic compounds can conduct electricity when they're melted. Another way to get ionic compounds to conduct electricity, our fourth property here, is to get them to be dissolved. Now we know that sodium chloride dissolves in water. Water is a molecule that has a polarity to it. One end of the molecule is slightly negative, that's the oxygen end, we call that the negative dipole. The other end of the water molecule is slightly positive, that's the hydrogen end, we call that the positive dipole. You can imagine that several water molecules would align their negative dipole so that they were near this positive ion. And the attraction between the negative dipoles of several water molecules and this positive ion would be enough to pull that ion off of that crystal. The positive dipole of other water molecules would do the same thing with the negative chloride ion and pull it off of the crystal. The process of breaking a crystal apart like that is called dissociation. Now those ions would become surrounded by water molecules. The positive sodium ion and the negative chloride ion would be surrounded by water molecules. That's called solvation for any solvent, and if we're talking about water as the solvent, it's called hydration. Now hydrated ions can flow through the material, through the solution, and as a result of that, we can have electricity, we can have the movement of charge. Electrolytes are dissolved ionic compounds. They're solutions that conduct electricity. Let's take a look at the properties of covalent compounds now, taking a look at the structure of covalent compounds first. If we have a nonmetal combining with another nonmetal, that would be two elements with high electronegativity, high attraction for bonding electrons. What ends up happening is they share those bonding electrons, those valence electrons. We get covalent bonding. Here's an example with water. Here's a water molecule. It's got a bent structure to it. The outline circle here represents the oxygen end of the molecule, an oxygen atom, and these solid circles represent hydrogen atoms. Now, across the bond between oxygen and hydrogen, electrons are not shared equally. That's a polar covalent bond. Oxygen has more electronegativity, so we would label that delta minus, and the hydrogen would be labeled delta plus. And because it's a bent shape, it's an asymmetrical molecule, across the entire molecule, there would be a polarity. We could say that this end of the molecule, the oxygen end, would be the negative dipole on the molecule, and the hydrogen end would be the positive dipole of the molecule. Now notice that the negative dipole of one molecule attracts the positive dipole of another molecule throughout the material. Attractive forces between molecules, or intermolecular forces, can take different forms for different types of substances, different molecular compounds. They can be dispersion forces, or dipole-dipole interaction, or hydrogen bonding. In the case of water, this intermolecular force is hydrogen bonding. So what happens if we cool the water down? Remember that if we decrease the temperature of a substance, that's decreasing the kinetic energy of the particles, or the movement of the particles. And at some point we would get to a temperature where the particles would begin to be locked in place by this intermolecular force. A crystal would form, a crystal of molecules, and we would have a solid. In this case, it would be solid water, ice. Notice that the intermolecular force between these molecules is much weaker than the ionic bonding that's holding together the ions in an ionic crystal. So we're going to get some different properties because of this. These four properties of covalent compounds are related to the fact that we have molecules that are held together by weak intermolecular forces, or held to each other with weak intermolecular forces. First, the phase of covalent compounds, whether they're solid or liquid or gas phase, varies. That's because there are various types and strengths of intermolecular forces. Remember, we talked about three: dispersion forces, dipole-dipole interaction, and hydrogen bonding. And there are other types as well. The second property is that covalent compounds have relatively low melting point. That's because the intermolecular force between these molecules is relatively weak. The third property is that we see covalent compounds are typically poor conductors. When we consider electricity, if we do separate these particles from each other, they're neutrally charged molecules. And if the particles are neutral, there would be no flow of charge. And then also, intermolecular forces can dampen any kind of transfer of vibration between the particles. And as a result of intermolecular forces between the molecules, we would see that there would be low particle motion and there would be poor thermal conductivity. So in general, we can say covalent compounds are poor conductors. Now, in terms of solubility, our fourth property is that solubility varies. Whether compounds mix together or not, whether they're soluble, can really be determined by this rule that like dissolves like. So let's take a look at some things that dissolve in each other. Polar and polar dissolve. So if you have water that's a polar molecule combining with alcohol that's a polar molecule, because they have like types of structures and intermolecular forces, they will mix with each other. Likewise, sometimes polar covalent substances will mix with ionic substances. For example, water and sodium chloride mix together. And nonpolar substances like oil or grease will mix with other nonpolar substances. For example, there are several types of situations where we will take oil and mix it with gasoline and put it into a fuel tank for an engine and try to lubricate the engine using oil that's in the fuel. Oil is nonpolar and gasoline is nonpolar, and that mixes together. Nonpolar and nonpolar mix, polar and polar mix, and sometimes polar and ionic mix. Now let's take a look at combinations where they won't mix. If you have polar and nonpolar, like water and oil, that will not mix. Things that feel oily and greasy to us are typically nonpolar. If you have polar and ionic, sometimes that won't mix. Like if you have water and you mix it with some sand. Sometimes it does, like when we have water and salt, sodium chloride, but sometimes not, like water and sand. And then finally, an ionic substance typically will not mix well with a nonpolar covalent substance. So in general, we can say that like dissolves like. Now, there's a couple quick side notes here. We said that intermolecular forces between molecules can make those molecules be liquid. It's actually pretty rare in nature to have pure liquids. Now, on the Earth, there are a lot of substances that are mixed in water. But the pure substance, water, and other pure liquids are actually pretty rare in nature. Consider that if the intermolecular force is strong enough, the particles get locked together in a solid, or if it's weak, the particles would typically be not attracted enough to each other and they would separate out and be like a gas. So in order for particles to be in liquid phase, the intermolecular force has to be big enough to keep the particles close to each other or in a condensed state, and weak enough so that they're not locked together in a crystal. That kind of sweet spot amount of intermolecular force is actually pretty rare. Consider that on the periodic table of elements, of the 118 elements that we have discovered so far, there are only two elements that are liquid: liquid mercury and liquid bromine at room temperature. All of the other elements are solid or gas. Another thing to consider, another side note here, is check out when we make this crystal of water how much empty space is present inside of that crystal. That's really, really odd in nature. It only happens with water and a few other substances that we've ever discovered. Almost all substances don't behave like this. The result of having all this empty space in this crystal is that solid water floats in liquid water. Ice floats on top of liquid water. That's really important for life on Earth, but it's really rare in the universe. For almost all other substances, when you turn them into a solid, they sink in their own liquid. All right, so if you understand what we talked about here for covalent compounds, you should be able to answer these 5 questions on properties of covalent compounds. Number 1, what type of force attracts one molecule to another? Number 2, why are some covalent compounds solid, some liquid, and some gas? In other words, why does their phase vary? Number 3, why do covalent compounds have low melting point? Number 4, a substance conducts electricity very poorly. Is that substance metallic, ionic, or covalent? And number 5, why does oil mix well with gasoline, but oil and water don't mix? Good luck.